DC generator working. So upon this completion of chapter, principle state the principle which machine convert the mechanical energy to electrical energy. That means a DC generator convert the mechanical energy to electrical energy, and discuss the operating difference between the different types of generators, and understand the principle of DC generator as it represents the logical behavior of DC motor. So by comparison of this topic, we can learn the how DC generator convert the mechanical energy to electrical energy. Overview of direct current machine, principal operation, construction, and types of DC. So the principal operation of DC generator: whenever a conductor is moved within a magnetic field in a such a way that the conductor cuts across magnetic lines of flux, voltage is generated in the conductor. The amount of voltage generated depends upon the strength of the magnetic field. That means the flux production. If the flux production is more, then the amount of voltage generated also more. The speed at which the conductor is moved, and the speed means the speed of the machine, the rotor speed is more, or the rotor is rotated by the prime mover. If the prime mover speed is more, the voltage generated also more. And third one is the length of the conductor within the magnetic field. The length of the conductor means it is the conductor. If length if the length of the conductor within the magnetic field is more, then the voltage developed also more, and the angle at which the conductor cuts the magnetic field also very important. At 0 degrees, 0 EMF. So it is increases from angle to angle. So the direction of induced EMF is known from the Fleming's right hand rules. The elementary generator, see the diagram. Simplest elementary generator that can be built is an AC generator. Basic generating principles are most easily explained through the use of the elementary AC generator. So this is the elementary DC generator, means a simple loop DC generator. For this reason, the AC generator will be placed. So this is not a DC generator. See the figure. In the figure, this is a simple loop generator. How the voltage is generating by the generator, that can be seen in this class. So the elementary generator means it generating AC voltage. AC generator will be discussed first. The DC generator will be discussed later. Because for AC generator and DC generator there is a small difference is there. So that difference will be explained later. An elementary generator consists of a wire loop mounted on the shaft so that it can be rotated in the stationary magnetic field. This will produce an induced EMF in the loop. Sliding contacts brushes contain connect the loop to an external circuit load in order to pick up or use the induced EMF. The pole pieces marked N and S provide the magnetic field. The pole pieces are shaped and positioned as shown to the concentrate the magnetic field as close as possible to the wire loop. The loop of wire that rotates through the field is called the armature. The ends of the armature loop are connected to the rings called slip rings. They are rotated with the armature. The brushes usually made of carbon with wires attached to them right against the rings. The generated voltage appears across the brushes. The brushes transfers power from battery to the commutator as the motor spins in later in a DC generator. The elementary generator, an end view of the shaft and wire loop is shown. At this particular instant, the loop of the wire, the black and white conductor of the loop, is parallel to the magnetic lines of the flux, and no cutting action is take place. Since the lines of flux are not being cut by the loop, no EMF is induced in the conductors, and the meter at this position indicates a zero. This position is called natural panel. The elementary generator B. The shaft has been turned to the 90 degrees clockwise. The conductor cuts through the more and more lines of flux, and voltage is induced in the conductor. At a continually increasing angle, the induced EMF in the conductor builds up from 0 to maximum value or peak value. Observe that from 0 to 90 degrees, the black conductor cuts the down, see in the figure, down through the field. At the same time, the white conductor cuts the up through the field. The induced EMF in the conductors are series adding. This means resultant voltage across the brush is the sum of the two induced voltages. The meter at position B reads the maximum voltage, maximum value. So after another 90 degrees of the rotation, the loop has completed 180 degrees of rotation and is again parallel to the lines of flux. As the loop was turned, the voltage decreased until it again reached to zero. From 0 to 180 degrees, the conductors of the armature loop have been moving in the same direction through the magnetic field. Therefore, the polarity of the induced voltage has remained the same. At 180 degrees also, zero voltage and a zero degrees also zero voltage. As the loop continues to turn, the conductors again cut the lines of the magnetic flux. This time, however, the conductor that previously cut through the flux lines of the south magnetic field is cutting the lines of the north magnetic field, and vice versa. See that? Since the conductors are cutting the flux lines of opposite magnetic polarity, the polarities of the induced voltage reverse after 270 degrees of rotation. The loop has rotated to the position shown, and the maximum terminal voltage will be the same as it was from A to C, except that polarity is reversed. So the elementary generator, after the another 90 degrees of the rotation, the loop has completed one rotation of 360 degrees and returned to the starting position, that is 0 degree. The voltage decreases from its negative peak back to the 0. Notice that the voltage produced in the armature is an alternating polarity. The voltage produced in is an alternating polarity. The voltage produced in all rotating armature is alternating voltage. At position A 0 degrees, position B 90 degrees, position C 180 degrees, and position C D 270, and A, that means again reverse. So at A 0 degrees, so at 0 degrees the meter shows that value is 0 because flux cutting is 0. And position B, the flux cutting is maximum in positive, and at C the flux cutting is 0, so EMF is 0 in meter. At D the flux cutting is maximum but in reverse direction, so at D maximum negative. Again A, So draw this diagram. The meter direction, the conductor of the armature loop, direction of the current flow. We can observe output voltage of an elementary generator during one revolution. So this is a simple loop DC generator. This is a simple loop DC generator. That means AC generator. That means AC generator only. It is a simple loop AC generator. So that was the AC generator. Now the DC generater. In place of slip rings, we can see here these are the slip rings at plus and minus. So the two slip rings are there, but in place of slip ring, if you go for commutator, the commutator is a wedge shaped copper segment, hot drawn copper segment. It's separated by the mica insulation. A commutator segments are placed on the shaft. The commutators are segments are rotated and brushes are not rotating. Since a DC generator must produce a DC current instead of AC current, in here we can see that AC output waveform, but we need a DC output waveform. So for that purpose we go for a commutator. A device must be used to change the AC voltage produced in the armature winding into DC voltage. This job is performed by the commutator. The commutator is constructed from a copper ring split into segments with insulating material. Between the segments, see next brushes against the commutator, brushes riding. That means the brushes are constant. Segments carries the power to the outside conductor circuit. The commutator in DC generator replaces the slip rings of the AC generator. So in a AC generator, slip rings are used, but in DC generator, commutators are used. The commutator also called a split ring. This means the main difference in the construction, the commutator mechanically reverses the armature loop connection to the external circuit. The loop is parallel to the magnetic lines of flux and no voltage is induced in the loop. Note that the brush make contact with both of the commutator segment. At this time, the position is called neutral panel. So this is the DC generator. As the loop rotates, the conductor cuts through the magnetic lines of the flux. The conductor cutting through the south magnetic field is connected to the positive brush, and the conductor cutting through the north magnetic field is connected to the negative brush. Observe that the conductor cutting through the south magnetic field connected to the positive brush, and the conductor cutting through the north magnetic field is connected to the negative brush. Since the loop is cutting lines of flux, a voltage is induced into the loop. After 90 degrees of rotation, the voltage reaches its most positive point. As the loop continues to rotate, the voltage decreases. Loop continues to rotate, the voltage decreases to 0. After 180 degrees of rotation, the conductors are again parallel to the lines of flux and no voltage is induced in the loop. Because at 0 degrees and 180 degrees, the flux cutting is 0. The rate of change of flux cutting is 0. So, EMF also 0. Note that the brushes again make contact with both segments of the commutator at the time when there is no induced voltage in the conductor, and there is no induced voltage in the conductors. Brushes again make contact with both segments of the commutator at the time when there is no induced voltage in the conductors. During the next 90 degrees of the rotation, the conductors again cut through the magnetic lines of the flux. This time, however, the conductor that previously cut through the south magnetic field is now cutting the flux lines of the north field, and vice versa. Since these conductors are cutting the lines of flux of opposite magnetic polarities, the polarity of induced voltage is different for each of the conductor. The commutator, however, maintains the correct polarity to each brush. The conductor cutting through the north magnetic field will always be connected to the negative brush, and the conductor cutting through the south field will always be connected to the positive brush. See that since the polarities at the brushes has remained constant, the voltage will increase to its peak value in the same direction. Again, during the next 90 degrees of rotation, the conductor again cutting through the magnetic lines of flux. This time, however, the conductor that previously cut through the south magnetic field is now cutting the flux lines of north field, and vice versa. As the loop continues to rotate, the induced voltage again decreases to zero. When the conductor becomes parallel to the magnetic lines of the flux, notice that during the 360 degrees, 0 degrees and 180 degrees, 0 and 360 is same. At 180 degrees and 360 degrees, the flux cutting by the conductor is 0. The rotation of the loop of the polarity of the voltage remains the same for the both waveform. This is called rectified DC voltage. The voltage is pulsating. It does turn on and off, but it never polarity for each brush remains constant. The output voltage is DC. See that here by the commutator segment we achieved the DC voltage. See the voltage waveforms at A, B, C, D and A, and it is repeated again. To increase the amount of output voltage, it is common practice to increase the number of turns of wire. Because number of conductors are increasing, then EMF also increases. The EMF will be increases with the increasing flux values and increasing the prime mover speed, and also by increasing the number of conductors in each parallel path in series to each parallel path. If loop contains 20 turns of the wire, the induced voltage will be 20 times greater than that for a single loop conductor. The reason for this is that each loop is connected in a series with the other loops. Since the loops form a series path, the voltage induced in the loops will be added. In this example, if each loop has an induced voltage of 2 volts, the total voltage for this winding would be 40 volts. Effects of additional coil. When more than one loop is used, the average output voltage is higher and there is less pulsation of the rectified voltage. Since there are 4 segments in the counted, only 2 brushes, the voltage cannot be fall any lower than point A. See that figure. The ripples is limited to the rise and between the points A and B. the graph by the adding more armature coils. The ripple effect can be further reduced. Decreasing ripple in this way increase the effective voltage of the output. The actual construction and operation of a practical DC generator differs somewhat from our elementary generators. Nearly all practical generators uses the electromagnetic poles instead of the permanent magnetic. If you use the permanent magnetic material, we cannot control the flux, but by the electromagnets we can control the flux. Permanent magnets used in our elementary generators. The main advantage of using the electromagnetic poles are increased field strength and possible to control the strength of the fields. By varying the input voltage, the field strength is varied. By varying the field strength, the output voltage of the generator can be controlled. Armature. More loops of the wire, higher rectified voltage. In practical, loops are generally placed in slots of an iron core. The iron acts as a magnetic conductor by providing a lower reluctance path magnetic lines of the flux to increase the induced of the loops and to provide a higher induced voltage. So this all we completed in the construction. Lap wound armature. And this is a wave wound armature. Lap wound armature windings are used for a low voltage high current application. Armatures are constructed with a large wire because of high current. Example are used in the starter motor of almost all automobiles. The winding of a lap wound armature are connected in parallel. This permits the current capacity of each winding to be added and provides a higher operating current. Number of current path A equal to P. P is the number of poles. Armature winding. Wave wound armatures are used in machines designed for high voltage and low current application. Their windings connected in series. When the windings are connected in series, the voltage of each winding adds, but the current capacity remains the same. Are used in small generator and hand cracked megometer. Number of current path A equal to 2. Armature winding. Commutator segments. Lap winding. A winding. Commutator. Field winding. Most DC machines use wound electromagnets to provide the magnetic field. Two types of the field windings are used: series field and shunt field. Series field and shunt field. Field windings are series field windings are so named because of connected in series with the armature winding, are made with relatively few windings turns very large wire and have a very low resistance. Made with relatively few windings, turns of very large wire and have a very low resistance. Usually found in a large horsepower machines wound with square or rectangular wire. The use of square wire permits the winding to be laid closer together, which increase the number of turns that can be wound in a particular space. Square and rectangular wire can also be made physically smaller than round wire and still contain the same surface area. Field windings. Shunt field winding is constructed with a relatively mainly many turns of small wire. Thus, it has a much higher resistance than the series field. Is inserted to be connected in parallel with R shunt, the same the armature. The high resistance is used to limit the current flow through the field. Field windings. When a DC machine uses both series and shunt fields, each pole piece will contain both winding. The windings are wound on the pole piece in such a manner that when current flowing through the winding, it will produce a alternating magnetic polarity. S is the here series field, F shunt field. Series field winding and shunt field winding. So the windings are two types: armature winding and field winding. The armature windings are again three types: wave winding, lap winding, and frog leg winding. So the wave winding, the number of parallel paths equal to, in lap winding, the number of parallel paths equal to P. Frog leg windings are used for at commutator to distribute the current. And field windings are self-excited and separately excited. In a self-excited series shunt and compound windings, the series winding because of series field, because of the field winding is connected in series to the armature, so it is called series field winding. Shunt field is because of the field winding is connected in parallel to the armature winding. Compound field because of a field winding is connected in series and parallel to the armature, then it is a compound winding. It is possible to have any number of poles depending on the size of the motor and the specific application it is being used in.